Trigonal planar. If all the atoms around it are the same, it has symmetry. So, all and I'll tell you why I'm saying this at the end because it has something to do with polarity. If it's tetrahedral, you've got symmetry as well. Okay. Do you know what I mean when I say symmetry? Like you can divide it, and the two sides sort of look the same. Okay. And they have an act like if you remember your math 11 and you're doing parabolas, you have an axis of symmetry down the middle. Both sides look the same. It's like a mirror image. Okay. Trigonal pyramidal does not have symmetry. Okay. No symmetry. And bent does not have symmetry either. If you have lone pairs of electrons, you don't have symmetry. Okay. Now I'm simplifying this a bit, but that's okay. All right, so why is this important? So we're going to look at polarity of molecules. Molecular polarity. So we have talked about bond polarity. Okay? A bond polarity is what is the charge distribution in the bond. Okay? So an ionic bond is the transfer of electrons, and we get full positive or negative charges. So the simple example that we always look at is sodium chloride. It's actually a sodium ion that gave up an electron to chlorine, and the electrostatic attraction between the positive cation sodium and the negative anion chlorine is what holds the the bond is the bond, holds the molecule together. Polar covalent bonds is the unequal sharing, and you get dipoles or partial charges. So we can do HCl like that. What's more electronegative, chlorine or hydrogen? Chlorine. So chlorine pulls the electron density towards it, and you get a partial negative charge on the chlorine and a partial positive charge on the hydrogen. So that is a dipole, two poles. And then non-polar covalent bonds is the equal sharing, and you get no charges. So the simple ones are when it's the same molecule, they equally pull, you don't get a charge separation. Okay? That's bond polarity. There is molecular polarity, which is the polarity of the entire molecule. What does the charge distribution on the molecule look like? All right. So this involves the shape of the molecule. All right. And all the different bond polarities being sort of summed together. So there's two results. All right. If you don't get a charge concentration in any one direction, you don't have a net dipole. Do you know what I mean when I say net? Like total, the overall charge, all right? And the charge and therefore the molecule would be non-polar. And then the other one is if you do have some sort of charge separation, you get a net dipole that exists and the molecule is polar. Okay? So for example, if I had, I'm just going to make this up. If I had B, I'm just not even using elements. Something like that, a linear molecule, okay? And A was more electronegative, and it's pulling the electrons that way, and this one is pulling the electrons that way. Those cancel each other out, okay? So the molecular polarity of this molecule is non-polar. But the bonds, these bonds are polar bonds, right? Does that make sense? It's a polar bond. When you just look at that, this is a polar bond. It's unequal sharing. But the overall polarity of the molecule is nonpolar. All right? And there's a fairly quick way to tell. All right? So when we represent bond dipoles, we use this sort of thing. So I should actually put that there. And this would be a negative, positive, positive, negative. Basically, it's an arrow with a little slash through it, indicating the dipole. Okay. Okay. See this first bit here? If it is an ion, it's polar. Cross that out. It's not true. Yeah, me and him had a discussion this morning. No. It's not a simple thing. Okay. If a molecule is symmetrical, okay, if it is symmetrical, it is non-polar. All right, because you don't get a net you don't get a net charge separation. They are distributed evenly. So if a molecule is symmetrical, it is non-polar. If it is asymmetrical, it is polar. And asymmetrical can mean you have a lone pair on the central atom. Okay? The easy way to remember this is the snap, which is symmetrical is nonpolar. So the S and the N, and asymmetrical. Oops. Is polar. Symmetry determines everything. Okay? And again, this ion, I'm crossing that out. Because I'm going to show you an ion that has a charge, it's an ion, but it's a non-polar. The molecular polarity is non-polar, which can be difficult to wrap your head around. Okay, let's look at a couple of examples. Boom. So we'll do a simple one. So carbon monoxide, carbon and oxygen. Look at the electronegativity difference. Oxygen's 3.5, carbon's 2.5. Oxygen wants to pull electron density. But when you look at the structure of carbon dioxide, so you would say that's what's happening, right? Those are the dipoles that want to happen. But what's the shape of this molecule? It's linear, right? So they cancel each other out. So this molecule is non-polar. It has symmetry, right? If I draw a line like this, both sides are the same. So as soon as it has symmetry, it's non-polar. Okay, that's your default. So symmetry, therefore non-polar. But these bonds are polar bonds, right? Because they're sharing electrons. Yeah, but you'd have to have different atoms, right? Yeah. Okay. And it wouldn't have symmetry then, right? So yeah, but that we're not. Again, all the exceptions, right? Just as an aside, chemistry is one of those sciences. It's like learn this, learn this, learn this, and then you go to university and you're like, oh, but here's the exceptions, here's the exceptions, here's the exceptions. So it's just physics tends to be like here's the laws of the universe, and they kind of for the most part everything follows that, right? Let's get into relativity and stuff, and things go weird, but for the most part everything just follows it. BCl3. All right, what's the structure of BCl3? It's a boron. It's three of the same atoms around boron, so it's going to be, yeah, it's going to be trigonal planar, because boron does not have um, a lone pair of electrons. If it had a lone pair of electrons, then it's pushing these bonds, and then it's no longer symmetrical. So as soon as you see that and it's symmetrical, you just say it's nonpolar. Now, if you had to draw the dipoles, it would look like this. Like chlorine's going to wants to pull the electron density, but they're all going to cancel each other out due to the symmetry of the molecule. Okay? Nonpolar because of symmetry. All right, here we go. What about this? We did HCl. Let's do NH3. NH3, ammonia. What is the structure of ammonia? Trigonal pyramidal, right? So it's this. I think it's even the example I used. All right, because it had ammonia, or sorry, nitrogen has a lone pair of electrons, so they push the bonds down. As soon as you do that, it's no longer symmetrical. So this is NH, one is coming out, one is going back, and you have a lone pair of electrons. It is not symmetrical. Therefore, it is polar. And what's more electronegative, the nitrogen or the hydrogens? Nitrogen's 3, hydrogen's 2.1. So if you were drawing the dipoles, it'd be like this. Okay? All right. So symmetry trumps everything. If it's got symmetry, it's non-polar, even though the bonds can be polar. Okay, so molecular polarity is different than bond polarity. All right, I want you to finish this page right here. So basically, there's the first one done for you. We did the Lewis diagram. I want you to give me the molecular shape. I want you to tell me if it's polar or not, and then tell me the intermolecular forces. So that's where it's London dipolar hydrogen. Okay? The last two, the two ions at the bottom are a little weird, so we can talk about those, but maybe you'll get those. All right? And I'll put the answers up in a sec.